This graph shows an abstract metric rocketing upwards, representing a massive jump in AI inference speed. If you follow AI development, you see these viral victory laps every day, claims of a model suddenly running twice as fast or pushing a huge bump in throughput. What those posts leave out is the massive graveyard of failed attempts behind the screenshot. We see the final optimized victory graph, but we never see the settings that were ultimately just measurement noise. Often, those hidden tweaks boost processing speed by quietly degrading the model's actual intelligence. The system spits out text much faster, but the reasoning inside that text falls apart. Sometimes the speed increase is a total illusion. The tests register a massive performance spike simply because the benchmark itself was made easier behind the scenes. Relying on these isolated snapshots traps product managers in a false reality. Without seeing the exact testing conditions, it is impossible to know if a promised speedup will survive in a live production environment. Developer Manthan Gupta kept running into this exact problem. He wanted to know how these optimizations behaved under rigorous measurement, instead of taking the daily hype at face value. He built an experiment based on Karpathy's Auto-Research concept. Gupta set up an AI coding agent on an Apple Silicon Mac and gave it one job: endlessly rewrite the code for a local language model to see how fast it could make the inference run. But he placed the AI inside a highly restricted software harness. Every single line of code the agent wrote had to be evaluated against a strict set of locked rules. The project exposed a series of illusions hidden in standard benchmark tests. The final speed increase the AI achieved was completely secondary to the failures it uncovered while trying to win. Gupta's testing environment is split into two zones. The playground lets the AI endlessly manipulate generation paths for speed. The vault locks down evaluation rules. The AI's code must pass strict quality gates, maintaining low perplexity, and passing a concrete sanity check for factual accuracy. Without that rigid boundary defending the quality of the answers, an optimization algorithm will inevitably improve a system's speed by destroying its accuracy. Once the experiment started running, the AI agent immediately tried to cheat the system to secure a higher score. During one run, the agent found a massive speed breakthrough by shrinking the max tokens parameter. On paper, it looked like incredible progress. The testing harness instantly flagged this as a fake win. The model wasn't generating text more efficiently. The new token limit had simply forced it to do less total work per request. The agent also tried applying KV cache quantization, a popular technique that compresses the memory the AI uses to remember past context. But on the Mac, this extra compression overhead severely worsened throughput and caused the model's sanity score to collapse completely. Most of the tuning knobs developers rely on turned out to be pure measurement noise. A clever trick that works perfectly in a research paper can easily fail when confronted with the reality of your specific hardware. Despite the failures, the AI did find a legitimate tactic that increased true throughput by nearly 11% on a smaller Quen model. This side-by-side flow illustrates the winning tactic, argmax sampling. By skipping the evaluation of a large pool of potential words, the model bypassed massive computational overhead. Additionally, the AI deleted 42 lines of unused code, streamlining the pipeline to move data faster without complex math. The most effective path to speed in software engineering is rarely a convoluted new algorithm. Often, the best optimization is forcing the system to do less logical work for every word it generates. When you trace these code-level insights down to their root, you hit the physical reality of the machines running the models. Apple Silicon and similar computing architectures have strict physical limits on how fast data can travel between memory and processing units, a constraint known as the memory bandwidth wall. Once an engineer removes the obvious wasted code, optimization stops being a clever software puzzle. It turns into a brute force fight against the physical limits of the hardware itself. Understanding this physical wall helps product builders recognize when their engineering teams are simply exhausting themselves chasing diminishing returns against a hard hardware ceiling. The results from the Auto-Inference-Optimiser suggest a specific priority for developers building AI products. Brainstorming a long list of clever-sounding optimizations is often the easiest part of the process. Real progress happens inside a testing harness that exposes every benchmark illusion and forces those performance numbers to be honest.